Well, hello everybody. Welcome back to another exciting JLam Bio video. I am JLam Bio, and today I am here to tell you about acceleration in motion with constant acceleration. I'm super excited to be here today. I am going to get you guys all revved up for acceleration in motion with constant acceleration. So we have a lot of student learning objectives for today. By the end of this video, you should be able to explain the concept of acceleration and calculate its value, understand acceleration and deceleration, calculate average velocity, use a velocity time graph to indicate distance traveled, and use equations of motion to solve for a variety of variables. So this is going to be a pretty deep lesson. It may run a little bit longer than expected, but break it down into short segments, get done what you can get done, and we will be ready to rock and roll. So we've talked a lot about velocity, we've talked a lot about speed, now we're going to focus on acceleration, and you've felt this because you've probably changed your velocity at some point today. Acceleration is just simply the rate at which velocity changes with time. Think about being in a car or an airplane, and you start out at 0, and then your velocity increases. When your velocity increases, you are accelerating. You feel kind of that jolt in the back of your body. It pushes you back a little bit. Even same thing when you're on an airplane. You can definitely feel it when velocity is rapidly changing as the engines are spooling up, preparing for takeoff. So acceleration occurs when there is a change in speed, a change in direction, or a change in both. So you don't feel the forces of acceleration when you are in a car going 60 miles an hour on cruise control. The reason being is that your velocity is constant. It does not change. But you feel it when you speed up or when you slow down. You feel that force on your body pushing you forward or pushing you back. Calculating acceleration is very easily. It's just the change in velocity, so the final velocity minus the initial over the change in time. Our units are in meters per second squared, and again, because we are using velocity and not speed, it has a direction, meaning that the value for acceleration can be positive or negative. An advertisement says that a car can go from 0 to 26.8 meters per second in 6.2 seconds. What is the average acceleration of the car? Well, remember that acceleration is equal to the change in velocity over the change in time. Our final velocity is 26.8 meters per second. And our initial is 0. And our change in time is 6.2 seconds. So again, we plug those numbers into our calculator and solve, and we get 4.3 meters per second squared. Do not forget your units. Okay, units are very, very important in this class, so please make sure you're putting down proper units here. A drag racer deploys a parachute and slows down from 130 meters per second to 45 meters per second. What is the acceleration of the racer? It's the same concept here, except we're slowing down. So our initial is this, and our final is that. So again, acceleration equals 45 meters per second minus 130. So remember, it's final minus initial, all over 3 seconds. We do our math and plug in and solve. We get negative 28 meters per second. Okay. So again, the concept of calculated acceleration is very straightforward. Just plug your numbers in and solve. Graphs can be very useful in determining acceleration, and acceleration can change with time, or it can be constant. So you can have instantaneous acceleration, which is an acceleration that occurs at any given time. You just, get the value for that. Constant acceleration is the acceleration the same every instant of time, and we're primarily going to focus on constant acceleration because it's much easier to calculate. We can then use a graph of velocity versus time to determine acceleration. The slope of the graph is acceleration, so if the acceleration that's constant, we're going to have a straight line here. So if we take a look, we start out at 0 and go up to 8 meters per second. Well, we have a constant positive acceleration. That is, the velocity is increasing over that period of time. If we have no slope, that tells us that we have no acceleration. Remember that no acceleration is not the same as no velocity. No acceleration just means there's no change in velocity, so we're staying at 8 meters per second. And then at time 7, we actually decelerate, which results in the loss of velocity over 3 seconds until we get to 0. Calculating the slope of these lines will tell you what the acceleration is, meters per second squared. You see the meters per second on the left and the seconds on the bottom. That's where we get that from. Deceleration is when velocity and acceleration are going in opposite directions. So speed increases when velocity and acceleration have the same sign. Speed decreases when velocity and acceleration have opposite signs. A ferry makes a short run between two docks. The ferry moves in a positive x direction with a speed of 7.4 meters per second. If the ferry slows to a stop in 12.3 seconds, what is its average acceleration? Well, again, acceleration, change in velocity over change in time. Remember that change in velocity is v final minus v initial. So if we take a look here, we want to slow that ferry to a stop, so our final velocity is going to be 0. So we just plug in our number. So 0 minus 7.4. Time is 12.3 seconds. Probably include our units here. Okay. What we're going to get at the end of that, when we divide, negative 0.60 meters per second squared. If the ferry returns to the original dock with a speed of 7.3 meters per second, if it comes to rest in 13.1 seconds, what is the average acceleration? Well, here's the thing to keep in mind. Again, positive direction this way, but we're returning, right? So we're going to have the opposite direction here. So the speed with respect to x is negative, right? Because again, we're talking about a positive x direction, so that means that this way is negative. Okay? So in this case, acceleration, we start our final velocity here is going to become 0 as well because it talks about going to rest. So minus negative 7.3 all over the time, 13.1 seconds. Okay. Remember that negative sign is due to the fact that we're looking in the positive direction going to the right, so we have to go negative when we go the opposite way. Now we plug that into your calculator. Two negatives make a positive, so 7.3 divided by 13.1. Our acceleration here is going to be 0.56 meters per second squared. So now we are going to be looking at equations of motion, and it's absolutely critical that you look at what information is given to you in the problem, because that is going to be helpful in you determining which equation of motion you are going to use to be able to solve for whatever you are looking for. So we've already looked at one equation of motion in the last unit when we talked about velocity. Now we're going to be looking and figuring out that we can determine velocity in relation to acceleration and time with the following equation, where the final velocity equals the initial velocity plus acceleration times time. And again, you can easily plug in values and solve for a variety of variables with this. It's pretty straightforward. So you throw a baseball upward with an initial velocity of 8.2 meters per second. Gravity gives the ball a downward acceleration of negative 9.81 meters per second squared. What is the velocity of the ball 1.5 seconds after it is thrown? So let's look at what information we have in this particular problem. We're given an initial velocity, so we have V1 or VI equals 8.2. We're given an acceleration due to gravity, negative 9.81. Sorry, I'll put some units there as well. And it wants to know the velocity, so it wants to know the final velocity, 1.5 seconds after it is thrown. So what I would do is I would look at my equations of motion and then figure out where do all of these variables fit in the equation and try to figure out what I'm looking to solve for. And if I look and find all of those, I'm going to use the equation we actually just last looked at. And then I just plug my variables in and solve. So I want to know my final velocity, so x equals 0.2 meters per second plus acceleration times time. And then you just plug in your values and algebraically solve for the unknown variable. And what we get is a final velocity of negative 6.5 meters per second. And since it is negative, that tells you that the ball is moving downward. We threw a baseball up, so that would have positive velocity. We now know that it's moving back down because our value here is negative. Okay? So again, pretty straightforward. Just plug your numbers in and solve for what's unknown. You'll always have the equations of motion handy, so it's really easy to look at what variables you have and figure out which equation of motion you are going to use. Average velocity is fairly easy to calculate as well. It's obviously just 1/2 times the initial velocity plus the final velocity. Kind of similar to finding the average of anything, right? We have two numbers, we divide it by 2, and that gives us our average. So we can actually substitute this in for the initial equation that we talked about in terms of velocity and placement to apply to situations where velocity actually changes. So in this instance, instead of having a constant velocity, we just have an initial and a final velocity. So we would just take the average of that and plug that in. So long story short, we basically take the equation on top and we plug that in for v in the equation below, and then we can solve for problems where velocity changes. So let's look at this problem. A boat moves slowly inside a marina with a constant speed of 1.5 meters per second. As soon as it leaves the marina and throttles up and moves with a constant acceleration of 2.40 meters per second. What is the velocity of the boat after it is accelerating after 5 seconds? So we're given a velocity. We're given an acceleration. Units, Joe. Units, units, units. I'll remember one day. And then it wants to know the final velocity. So that first one must be our initial. After a time of 5 seconds. So again, I can actually just plug this into the first formula that we took a look at here. So I'm going to use VF equals VI plus A times T. Plug in my unknown variables, or my known variables rather. 1.5 plus acceleration, 2.4 times T, which is 5. And I solve and I get a value of 13.5 meters per second. Okay. Now it wants to know how far the boat has traveled in that time. Well, we have changing velocities. So as a result, we're going to just use the previous equation that we looked at, but the only difference here is that we are going to plug in average velocity for that. So remember that our previous formula, xf, xi plus 1/2 vf plus vi times t. And we have all the variables that we need. We're just looking for how far the boat traveled in that time. So x of f is our unknown. Our initial spot, we'll call that point 0. Okay, because again, we're looking at a point where we started to the point where we end, so this is going to be 0. And then we just plug in our other variables. So VF is 13.5 plus 1.5. And we're all going to multiply it by 5 seconds. I plugged all those numbers in and solve, and what we get is 37.5 meters. Okay. So again, it's just all about setting up the equation appropriately, plugging in the correct numbers, and solving for what you know. Let's move on. Another really nice feature of the velocity time graphs is that we can actually determine the distance by looking at the area under the curve itself. So in order to solve for the area under a curve here, I would probably draw a line, a vertical line, at 2 for time. And that would give me a square that would be 4 times 2, so the area of that would be 8. So keep that in the back of our mind. And then we would have a right triangle starting at 2 and ending at 4 in terms of time. And remember, the area of a triangle is 1/2 base times height. So 4 times 2 times 1/2 would be 4. So I would add 4 and 8 total in order to get 12, and that is the distance in which an object has traveled. You'll see what we mean in the sample problem here in just a moment. So let's use the same principles before to try to determine the the distance of this particular object and utilizing this particular chart. So I'm going to try to just make this into as many simple shapes as possible, making it much easier to determine the areas. Okay. So if we take a look at this one here, part A, okay, we're looking at a triangle, so that's going to be 1/2 base times height. So that's going to be 1/2 of 30 times 2. Okay, so what we get for A, I'll just put those over here, sorry. 30 meters. B is pretty simple. B is a square. So that's just 30 times That's going to be 3. So part B, you have 90. For C, we got 3 times 30 again. So that's also 90. And then for part D up here, because again it is a triangle, we'll just do 1/2 base times height. So the base is 3, and the height we go from 30 to 50, so that is 20. So 3 times 20 is 60, times half is 30. And then to determine the distance traveled, we're just going to add all those up. So the total distance here, 240 meters. Okay. So again, it's just simple math here, being able to plug in and calculate. And again, breaking this graph down into smaller shapes and sizes makes that a whole lot easier to be able to calculate. Let's move on. So a couple more equations that we want to make sure that we understand. Here's an equation below that we can relate acceleration, time, and position with the following function. And then we can also recognize that acceleration causes velocity to change with position. So again, we're just looking for what information do we have and what are we trying to solve for. Again, you'll always be given these equations. You just need to make sure that you know when to use them. And again, that is all based off of what information is given to you in the problem itself. Let's look at 2 more example problems, and then we'll review equations of motion and call it a day, because I know this video is pretty heavy. A drag racer starts from rest and accelerates to 7.40 meters per second. How far will it travel in 1, 2, and 3 seconds? So we're starting from rest. So we have our initial position, which is 0. We have an acceleration. And we're given 3 different times. And it wants to know how far will it travel. So that's going to be final. So I need to look for an equation that has all of those different variables in it. And fortunately, we have one. Okay. Now some of these variables are going to be 0. This is, again, we're starting from rest, so our initial velocity is also 0. So here I can just plug in and solve. These are going to cancel because anything multiplied by 0 is 0. And then your final velocity is just 1/2 times 7.40 times 1. 3.70 meters. Okay. And again, you repeat that exact same process. So for 2, you would just mark that out, plug in a 2, and then you would get 14.80 meters, and then do the same thing for 3. Okay. So this bottom one here, park ranger sees a deer frozen in the headlights above. The ranger is driving at 11.4 meters per second, so we have an initial velocity. Immediately applies the brakes to decelerate, so we have an acceleration. That's negative because we're decelerating. How much distance is required for the vehicle to come to rest? So here, since I want to know distance, I'm going to use since my velocity ends, it's going to be 0. So we're going to just plug those numbers in and solve for delta x. Again, algebraically manipulate the equation. And we get at the end is delta x, 17.1 meters. So again, I know it's a lot, but you just need to make sure that you're able to simply plug those numbers in and solve and figure out what the question is looking for, what's given to you, and then what the question is asking for, and you'll be able to solve these relatively easily and quickly, hopefully. So the last thing I wanted to provide you is a table with all of these equations in motion. So if you take a look at all of this information here, you really want to be able to focus on what variables are related in these, because that's going to be very helpful in helping you determine what equation you are going to use. You'll always have these equations to be able to use to be able to solve for the problems, but you do need to make sure that you understand when and where to use these 5 equations of motion. We will practice this quite a bit, as I'm probably going to give you a little bit of extra time on this week's assignment in order to be able to figure things out a little bit easier, since this was such a long video. Hey, thanks again, guys, for everything that you do. I really appreciate all your hard work so far, and hopefully by the end of this video, you've gotten all this information. It may not be down perfectly yet, but again, practice makes perfect, and we're practice. All right, guys, I'm going to talk to you later. Have a great day. Wish you best of luck. Make sure you like, comment, subscribe, and we will catch you next time. Have a great day, guys. Bye-bye.